Operations with complex numbers. That just means arithmetic. In this video, we'll add and subtract complex numbers, multiply complex numbers, divide complex numbers. We'll find a pattern in the powers of I, and we'll square some complex numbers just for practice. Remember that a complex number has a real part and an imaginary part. So when I want to add two complex numbers, like 3 plus 2i plus negative 4 plus 5i, I want to add the real parts, their like terms, and add the imaginary parts, their like terms. So when I combine here, my sum, 3 plus negative 4 is negative 1, and that's the real part of the sum. And 2i plus 5i is 7i, and that's the imaginary part of the sum. For a subtraction, 9 plus I minus 3 minus 5i, I'd like to change it to an addition before I start. So I'm going to change the subtraction to addition and change the sign of both of the parts of the second number. Now I have a real part, 9, and a real part, negative 3. That gives me 6. And I have an imaginary part, I, and another imaginary part, 5i, which gives me 6i. If we're multiplying complex numbers, here's an example. 3i is multiplied by 2 plus 7i. We're just going to use the distributive property. 3i is going to be multiplied by 2, and 3i is going to be multiplied by 7i. Well, 2 times 3i is 2 times 3 times I, or 6i. And 7i times 3i is 7 times 3, 21, and I times I, which is going to be negative 1. 6i plus 21 times negative 1, or negative 21. And I want to write it in the form real plus imaginary. So I'm going to have to switch those two around. The real part here is negative 21, and the imaginary part is 6i. If we're multiplying complex numbers that have both real and imaginary parts, we have two binomials, and we need to do double distributive property, or FOIL. 4 times negative 2 is negative 8, and 4 times negative I is negative 4i. 3i times negative 2 is negative 6i, and 3i times negative I is negative 3i squared. Since I squared is negative 1, this last term should be simplified to be negative 3 times negative 1, or positive 3. Now we have negative 8 and positive 3 as the real part of our result. It's negative 5. For the imaginary part of our result, we have negative 4i minus 6i, which is negative 10i. The important step to remember here is to convert any I squareds to negative ones. There's one more multiplication I want to show you because it gives us a useful result. These two complex numbers, 8 minus 5i and 8 plus 5i, are called conjugates. When we multiply conjugates of complex numbers, we get a real number back, and that's going to be useful for division. So I'm going to multiply 8 times 8, that's 64, and 8 times 5i, that's 40i. And now comes the great part where the middle terms cancel out. Minus 5i times 8 is minus 40i. And minus 5i times plus 5i is negative 25i squared. It's important to remember to change that I squared to a negative 1. Negative 25 times negative 1 makes this a positive 25. Our terms in the middle will cancel each other out because of this conjugate property, and so we have no imaginary term left. What we have is the square of 8, 64, and the square of 5, 25. 64 plus 25 is 89, and it has only a real part, no imaginary part. Here we're going to divide negative 1 plus 3i by 4 minus I, and to do that what we're going to do is multiply by the conjugate of the denominator. Since the denominator is 4 minus I, the conjugate is 4 plus I, and I'm going to multiply by the same thing on the top and bottom of the fraction. Because 4 minus I and 4 plus I are conjugates, their middle terms are going to cancel out. So I'm going to have 4 times 4, 16, minus I times plus I, minus I squared. And that's 16 minus negative 1, or 16 plus 1, gives me 17. If I multiply the top numbers, negative 1 plus 3i times 4 plus I get negative 1 times 4, negative 4. Negative 1 times I, negative I. 3i times 4, 12i. And 3i times I, which is 3 times I squared, or negative 3. Negative 4 plus negative 3 is negative 7, and negative I plus 12i is plus 11i. So I've multiplied out the numerator and denominator, but I still don't have the form a plus bi. To get that, I just have to write each part of the numerator with a denominator of 17. The real part, a, is negative 7 over 17, and the imaginary part is 11 over 17 times I. The powers of I form an interesting pattern, and because of that, we can easily evaluate very large powers of I. So I to the 1 power, of course, is just I, and we know I squared is negative 1. So I to the 3rd, which is I squared times another I, is negative I. And I to the 4th is negative I times another I, or positive 1. You could also think of it as I squared times I squared. That would be negative 1 times negative 1. So I to the 4th is 1, and now that it's a 1, it's just not going to affect any future multiplications. So that means that I to the 5th, which is the same as I to the 4th times 1 more I, is really a multiple of 1 times I. I to the 5th is the same as I to the 1. It's equal to I. And I to the 6th, if we think of it as having an I to the 4th, which is just 1, then it's I to the 4th times I squared. And so 1 times I squared is the same as I squared. It's negative 1. And so forth. When we get to I to the 8th, we have I to the 4th times itself, and that is just another 1. So I to any power n is equal to I to the remainder when n is divided by 4. If I try I to the 243rd power, I just have to divide 243 by 4, and I get 60. Remainder 3. Well, the remainder is the important part. I to the 243 is the same as I to the third. It's equal to negative I. I to the 105 is the same as I to the remainder when 105 is divided by 4. That remainder is 1, and so I to the 105 is the exact same thing as I to the 1. It's I. Be careful taking powers of complex numbers. Exponents don't distribute over addition, so 1 plus 5i squared is the same as 1 plus 5i times 1 plus 5i. These are not conjugates. They're duplicates of each other, and the middle term is not going to cancel out. So we have 1 times 1, that's 1, and 1 times 5i plus 5i, and we have 5i times 1, another 5i, and 5i times 5i, which is 5 times 5, 25, times I squared, is negative 1. When we combine like terms, we have real part 1 and a real part of negative 25. That gives us negative 24. And we have imaginary parts of 5i plus 5i, which is plus 10i. So the result when we square 1 plus 5i is negative 24 plus 10i. I have one last example of squaring for you. It's a little challenging. We have the square root of 2 over 2 plus the square root of 2 over 2i. So we want to square that, and that means we're going to multiply it by itself. Now you can see that we're going to have to multiply the square root of 2 over 2 by itself several times here. So let's figure out what that is. Square root of 2 times square root of 2 is square root of 4, and 2 times 2 is 4. So that's 2 over 4, or 1/2. Now that we know that, let's multiply this out. So I have a square root of 2 over 2 times itself. That's going to give me 1/2. And I have a square root of 2 over 2 times square root of 2 over 2i. That's going to give me 1/2i. I have that same multiplication again, so I have another 1/2i. And then finally, I have square root of 2 over 2i times itself. So that is 1/2i squared. I squared is negative 1, so it's negative 1/2. Well, my real parts, 1/2 and negative 1/2, cancel out here. And so all that's left is this imaginary part. 1/2i plus 1/2i is 1/2i. This square root of 2 over 2 plus square root of 2 over 2i, when we square it, we get I. So that tells us that the square root of I is equal to this complex number, square root of 2 over 2 plus square root of 2 over 2i. That's kind of cool.